Okay, so let's go ahead. Okay, so this time I'm going to do things a little differently. I'm not going to give up until 7:30, so 2 minutes and 30 seconds. I'll give you guys up until, I'll give you another 30 seconds. So I'll give you guys until 7 minutes are left on the timer. So I'll be back. Sure, I can do a couple more summation. For the most part, we cover most of them, but I'll do a couple. We did most of the variations, but I'll do a few. Okay, so let's go ahead. So I'm just gonna start recurrence, and then we'll go for the rest. Yeah. Can you practice? Yeah, definitely. Hey, dude, website's up, dude. You got all the time in the world. Not all the time. You got a couple days left, but
48 hours.
Yeah, 48 hours. So, but I hope it's helped you improve the website and the videos so far. But okay,
Oh yeah,
so
it's been a heaven send. Thank you so much for that.
yeah, no problem, man. No problem. Gotcha. Okay, so you guys know the drill. I'm gonna give you guys 2-3 minutes to work on this, and then we'll hop into the question. So when this hits 7:30, I'll hop in. Okay, so use the iteration technique to find the big O recurrence relation below, or for the recurrence relation below, you may find the following results useful. Okay, so again, whenever you see these type of setups, if you see this, you're on the right track. So yeah, let's get started. So let me just write down everything real quick.
Are all the types of questions like this going to have the equation written out, or can they give us like a word problem and then we have to figure it out?
So there's some where they'll give you code, and then it's more like algorithm analysis kind of questions. They'll give you the code, and then they'll ask you to, like try to prove your answer. And yeah, in those you would have to derive it yourself. But generally they're kind of easy from what I've seen. Like they'll ask you something that's like merge sort, where it's going to be something like 2 t of n plus o of n, because then it's like n log n or whatever. But or it might be just o of n and squared, etc. So yeah, let's get started on this. Oh yeah, and let me just write these extra things on the side in case we run out of time. Okay. Okay, so we have this recurrence relation. So first things first, we always do our 3 iterations, because that way you can secure 6 points, at least 5-6 points, assuming you do all your algebra right. So what that's going to end up looking like, let's do it. Okay, I cannot control my whiteboard. 1 second. Okay, there we go. Okay, so we're going to do our 3 iterations. So before, what I would do is I would define what each recursive call is going to look like. But, I'm assuming you guys have watched my previous video on recurrence relations. So I'm just going to go through the steps right then and there. So this is our starting point. And now what we're going to do, we're going to model what the recursive call is going to look like. So we have 2 times 2 t of n. This, if we're dividing by 3 in the next layer of the recursive call, so in the next recursive call, if we're dividing by, let's say this is n right here, if we're dividing n by 3, then in the next recursive call, we're going to divide it, for example, by 9, if you think about it. So if you divide it by 3 in the next recursive, we're going to have 9. So you're just going to square it. So right here is going to have 9, then plus. And this O of n, one thing you can do, you can just think of it as n. You don't have to keep it in this format, just keep it as n. But in this case, one thing that I've told you guys is whenever you have like a recursive step where there's some sort of n after your recursive call, you're just going to transfer what was here, just transfer it downwards into that n position. So now we're going to have n over 3 plus n over 3. Right, then plus n, because remember this n is still on the outside. So now we're just going to distribute it out. Plus 2 times 2 over 3 times n. Just distribute this out right here. And now we have this plus n out on the outside. So far, so good. Now let's do another iteration. So we're going to do the same exact thing. 2t. So we were at 9. And since we're squaring, so we're doing 3 times 3 times 3. 3 times 3 times 3 is 27. And we're going to do plus. And like I said, just transfer this over into whatever this n variable here is going to be for the next recursive call, which that's just going to be n over 9 plus 2 over 3 plus n. And we just distribute this out. Plus 4 divided by 9, n. Oh yeah, I forgot the n here as well. 2 over 3n plus n. Okay, so this is what we have after the third iteration. So at this point, we have 6 points out of all the ones that we can get. You just do the 3 iterations and you're good. But one thing I would recommend you guys to do, unless you're like really good at these, write down your general form. And the way you derive the general form, gone over it before, but you just look at the trend of how the numbers are changing. So one thing I like to do personally is see, is there anything that I can pull out? Is there any sort of common term in another group of terms? So what I mean by that, notice how out of all of these 3 values, this is actually 1 over 1 because anything can be itself times 1. So this is 1 over 1, 2 over 3, and 1 over 1 n, 2 over 3 n, 4 over 9 n. So what I like to do is I like to order them in a certain way. So I'll do 1 over 1 n plus 4 over plus 2 over 3 n plus 4 over 9 n. So now we can see kind of a sort of trend right here. But first things first, let's remove the n. Since this is a common term, we can just pull it out of all of these variables because it's actually multiplied against all these variables. So this is the setup we're working with right now. So you can just distribute it and you'll get exactly what you have up here. So now let's see how is everything changing. So we go from 1 to 2, that's times 2, and then 1 to 3 times 3, then 2 to 4 times 2, 3 to 9 times 3. Okay, so we can see that on every iteration, we're changing 2 over 3, right? We're just 2 over 3 times 2 over 3, etc. So now we have that information. So we know that this summation is going to be something related to 2 over 3. And what's happening? Every time we're multiplying something 2 over 3 times something that came from a 2 over 3, meaning this term is getting squared, or sorry, it's to the power of something. So here, any element, when we have a 1 over 1, any element such that, like, let's say you have an element b, any element to the power of 0 is just always equal to 1. So this is how you get this. So you know a summation, or this sequence of values that you're adding, you know, we have the pluses here. They're all, it starts from I equals 0, because if not, how else would you get a 1 over 1? If then it ends up turning into 2 over 3, 4 over 9. So we start at I equals 0. Okay, I equals 0. You just erase the white thing I just drew. There we go. So I equals 0. And then now we go I equals 1. And we end at I equals 2. This checks out because if you end up squaring this, you get 4 over 9. So we're good. We know that the last iteration, and this is important to these type of questions, the last iteration of the summation is going to be this term right here. And what we can do with that is see, okay, it ends at I equals 2. So the last iteration is going to be 2. So that's going to be relevant. So let's just store that information. Last summation iteration is 2. So this is important, and I'll show you why. This is part of deriving the general form, which is, you know, the whole trend of how it's changing. So now we have this whole part set up. We're all good. We're going to come back to that. So let's look at these two terms right here. So you've probably seen these numbers and bases enough to know what they are, you know, when it comes to like powers. These questions, they always follow powers in some sense, always. So right here, this is 2 to the 3. Right here, this is 3 to the 3. So this is iteration 3, right? Let's see the second iteration. Second iteration, this is 2 over 2. Second iteration right here, this is 3 over 2. Okay, so we see there's something going on with this right here. These two numbers, they're being ran by the same value, right? So this is really your k, because that's what ends up changing. So that's important. And in the main iteration right here, in the beginning, it's just 2 to the 1, and then we have a 3, so that's 3 to the 1, right? So we go 2 to the 1, 3 to the 1. Then we go 2 to the 2, 3 to the 2, 2 to the 3, 3 to the 3. And that's where we're at. And notice we're in our third iteration. So we can say that this number, our k currently is 3, right? So our k is 3. And the reason why I said, well, we needed to evaluate these numbers right here is because that's going to tell us what the summation is going to be going up until. So I'll explain that in a second. So we know that these variables are changing based on, you know, an arbitrary number k. So this is going to be 2 to the k times t n over 3 to the k. Okay, so we have this part set up, right? But we have all of this stuff right here. So how can we simplify that out? So let me just write this down here. And over 3 to the k plus, and we still have this n on all of them. So notice how our iterations, our k is 3, right? So these variables are 3 currently. This summation is going up until 2 because the last term is 2/3 to the power of 2. So what do you think it's going to be running on? It's going to be running based on k minus 1. Because remember, when you do a summation, let's say you have a summation, for example, 5i equals 1, right? The last term, you end up going I plus 1 plus 2 plus 3 plus 4, and you also include, remember this bound is inclusive, you also include plus 5. So what that's telling us, if the last iteration is 2 and our k is equal to 3, what are we going to be running up until? K minus 1. So this is really times k minus 1. I starts at 0. We confirmed that because we have 1 over 1. And then what is the term that's changing in each summation? It's 2 over 3 to the power of I. Because notice we have, let's assume k is 3. Then this is going to go from 0 to 2. And that gives us all of these terms right here, this summation right here. And we can make sure that it's running based on k because we can just go back to the previous iterations. So this is a good way to check if you know you're on the right track. So at iteration 2, when k was 2 right here, we can see that these terms, we only have the terms 1 over 1 plus 2 over 3. So this is I equals 0, and this is I equals 1, right? The last term is I equals 1, but k is 2. So we can see that as you keep going through the iterations, it's bounded by k minus 1. So right here, k minus 1, 2 minus 1 is 1, which is, this is why this last iteration. When k is 3, you go k minus 1, which is 3 minus 1, meaning 2. So you only go up until 2 over 3 squared, which is 4 over 9. So I hope that makes sense right there. Okay, so that clears that up right here. So at this point, we've established how we got to this general form. But there's one last thing. Whenever you have some sort of geometric sum and the value right here is less than 1. So let's call this letter or this value in here R. If R is less than 1, then what you're going to do, I'm not going to explain it. It's like a whole calc thing, but you're going to end up converting this into an infinite sum. So this is where that formula they tell you about comes in. So we have summation I equals 0, 2 over 3i to the power of I equals 3, but it's infinite. So again, whenever this value right here is less than 1, then you just add it in there. For those that know calc, it's because it converges eventually. But okay, so we're just going to make that quick replacement. Let's just do that. Not really going to change much. Okay, so now how is this going to change? We know that this whole summation right here is going to be equal to 3. So we can literally just remove this. And we have 3 times n, so let's just rewrite it as 3n. Okay, so this is what we're working on right now. This is our final general form. Now from here, we can start solving stuff. So now once you have your general form, let's see what the base case is. T of 1 equals 1. So what we're going to do, we're going to get T of n over 3 to the k, and then T over 1. We're just going to take these two terms and set it equal to each other. N over 3 to the k equals 1. That gives us n equals 3k. That also gives us, if we write it in log form, log base 3 of n equals k, because you do 3 to the power of k equals n. So we have that information now. So let me just copy this over to the side real quick. Okay. So now at this point, we can start solving for stuff. So we know that 3k is equal to n. So what we can do, we can plug in n for this right here. And think about it. If we plug in n for this right here, we have t, or we can plug in 3k right here. But if we plug in the same thing, let's just call it n, or 3 to the k over 3 to the k. In both scenarios, this just becomes t of 1. And we know from our base case up top, t of 1 is equal to 1. So we're just going to plug in t of 1, meaning 1, for this right here. And in that case, all we really have to do is just remove it because, 1 times anything is just itself. So as of right now, this is what we're working with. So we remove the times 1. And we still have a k. The entire goal of this, remove your k's, which is another reason they changed the thing to the infinite sum as well, I guess. But so now we have a k. Let's see what k is equal to. K is equal to log base 3 of n. So we're just going to plug that in for this right here. So yeah, it's going to look disgusting, but this is part of solving it. And now let's go up. Remember, this appeared. They gave you this. So they said, hey, it might be useful. So we have 2 to the power of log base 3 of n. We have that. And we set it equal to n to the log base 3 of 2. So n to the log base 3 of 2 plus 3n. Okay. So this is what we're working. Oh wait, this was 2. Sorry. Let me just make sure of that real quick. Yeah, it was 2. Okay, so now at this point, I think I've done a problem similar to this before, but now we have to see, okay, which term is larger? So this is where your log rules come in a little bit more. So let's think about it. We have 2 terms. We have n to the log base 3 of 2. And we're trying to find the big O. So we want to see which one is like the overall largest. So we have this, and then we have n, but remember, anything just on its own like this is just whatever it is to the power of 1. So n to the 1 versus this. Which one is bigger? So let's think first in terms of different numbers. So let's think, okay, what is equivalent to 1? How can we get some sort of log base 3 equal to 1? So we can use 3 because this equals 1. The weight equals 1. 3 to the power of 1 equals 3. So that checks out. You're good. Okay, so we have this term, this is equal to 1. And just for reference, let's see how we can get something base 3 equal to 2. We can set it to 9 because 3 to the power of 2 is 9. Okay, so now we know that as this number here increases, so as this number increases like it did from 3 to 9, this value also increases, meaning this could be, for example, log base 3 of 6, and it's going to be, we know it's going to be somewhere between log base 3 of 3 and log base 3 of 9. So it's going to be somewhere in the middle, not exactly either because we already have definite answers for either, but it's going to be somewhere there. We can apply the same logic to this one right here. If as this value in here increases, we know that whatever exponent is going to be also increases. So if that applies in that sense, then it also like it's this is going to apply, just so you guys know, as you go down. So as you go down the logs, then this value is also going to go down because the exponent is going to have to be raised to is smaller. So if you do, for example, 3 to the 3 log base 3 of 1, this would equal 0 because 3 to the 0 is equal to 1. So clearly, right now, we can clearly see that for us to have log base 3 of to the power, or log base 3 of 2, it would have to be somewhere in this region between log base 3 of 3, which equals 1, and log base 3 of 1, which equals 0. So it can't be either of them, so it has to be in the middle. And if it's in the middle, we know that 1 is greater than this term, like the power of n. So I hope that makes sense, because this is 1, right? But this is something from log base 3 of 1 to log base 3 of 3, which essentially just means it's something in this range right here. So from 1 to, or sorry, from 0 to 1. Meaning, if it's neither and it's in the in between, it is less than 1 because 1 is excluded. It's greater than this term. So this term is somewhere between 0 and 1. But that's how you can tell which is a dominating term. So the dominating term is just n to the power of 1, which is just n, and that gives you big O of n. So that's how you can derive that. So let's go back to that. So let's see what the answer was. Yeah, so they did the same iterations. They had an n. They set it to infinity. And they also plugged this stuff in, so they have the same point. And they follow the same logic. Log base 3 equals 1, so it must be less than, therefore it's just log of n. So that's how you end up deriving this one. So I'm going to go another one of these, and then we're going to switch off from this topic. Okay. So I'm just going to hop into this one right away. Okay, so we have T of n is equal to T of n over 2 plus 1 for all n greater than 1. And we also know that T of 1 is equal to 1. Okay, so let's give it a shot. Find a tight big O answer. All right. So first things first, 3 iterations, 6 points right off the bat. So let's try to do it a little quicker than the previous. So let's see. Okay, so it's dividing by 2. If it's dividing by 2, then that means we're going to also divide by 2 more. We'll just multiply this denominator by 2. Then we have our plus 1. Notice how this is not an n, so you're not going to be plugging in n over 2 here. It's just plus 1. So that's something to watch out for. Then we have our plus 1 on the outside. Distribute. yeah, and always, as I always say, just keep this, start collecting these numbers because you'll see a pattern from them later on. Oh wait, I actually forgot a 2 right here. So this is 4. There we go. Yep, all good. So let's keep going. Next iteration. 4. 2tn over 8 plus 1. Now we're going to have this right here, the trailing summation. Honestly, what I think you guys should do is write this first because a lot of people might forget that. So definitely just write this out, and then do this part because a lot of people always forget that, and that will make it like very, very difficult, if not like impossible to see it if you forget it. So 2t of n over 8 plus 1. There we go. Distribute the 4 to the 1 plus 4 plus 2 plus 1. Okay, so let's do the same thing that I've told you guys to do for all the other problems. Let's reorder these, right? So if we reorder them, I'm just going to keep it on the side. So let's reorder to make it look nice so we can see the trend. So we start off with 1, then we ended up with a 2, then we ended up with a 4. Okay, so clearly we can see times 2 times 2. So we're changing on a basis of 2. Okay, so if we're changing on a basis of 2, that means that we're doing 2 times 2 times 2. And if we do another iteration, it's going to be 8. So yeah, we'll just leave it here. But just for reference, if you think about it, if we do another iteration, it would look something like t of n over 16 plus 1. And when you distribute this, it would be 8. So we have 8 plus 4 plus 2 plus 1, which you see what's happening. There's a power of 2 in this summation. So the value is going to be 2 to the power of I. So let's think about it. How can we get 1 from times 2? So is I to 2 to the 0, right? So this is I equals 0, 2 to the 0, I equals 1, I equals 2. 2 to the 1, 2 to the 2. Okay, so again, the last term we see is going to give away what the upper bound is. That's very, very important. And we're going to check this against k. So let's just write this down. Last I equals 2. So now we've kind of analyzed this part of it. Let's try to find what our k might be right now. So we're going to look at this part right here. It's part of the equation. You notice that this 8 is equal to 2 to the 3. This 8 is also equal to 2 to the 3. And let's keep track of whatever the exponent is. So we have 3. That's good. Let's go to our previous iteration to make sure, what our idea is correct. This is 2 to the 2, 2 to the 2. Okay, so it looks like things are moving based off of like they're both moving at the same step. There's somewhere this one's like 2 times 2 to the 2 or something weird like that. But in this one, it's a simpler one. And let's go back to the very first one. This is 2 to the 1, 2 to the 1. Okay, so now we're seeing how things are changing. So in this current iteration, we know that k is equal to 3, right? So now that we have our k, we know what our k is where we currently are. Let's look over at our summation. If the last term we processed was 2, the last term we added, remember summations are inclusive, that means that our upper bound must be equal to k minus 1. If k is 3, 3 minus 1 is equal to 2, meaning this is the top bound of our summation. And again, you can make sure of this in the previous iteration. When k is 2, we only go up until 2, 0 plus 2, 1, which is 1 plus 2, which we have right here. So we know that the top bound is k minus 1.
Can't you just do 2 to the k minus 1? Like if you added all of them, like you would see that it's like 7, 3, and then 1, which is just 2 to the k minus 1.
That's a final formula if you do like the x to I, etc. But some people might not be able to see that, so that's why I'm going through this whole part. And yeah, like personally on the test, I would not be doing all this, but I'm just showing you guys how to think about it, how to check your work, etc. So yeah, you can also use that formula. But now that we've seen the trend in the top bound is k minus 1, let's plug it into summation form. So we know top bound is k minus 1, I equals 0, and it's going to be 2 to the I. Okay, so this part is good. And we know that these portions right here, they're based on 2 to the k, because this term is right here is k, and this right here is going to be, so this is our general form that we're building, n over 2 to the k. And just like he had mentioned, there's a formula that you can use. If you can see it, you can see that these terms right here, this is in total is equal 7. 7 equals 2 to the k minus, or sorry, 2 to the k minus 1. So 2 to the 3, 8 minus 1, 7 equals 7. That checks out. But for those that might not be able to see that, this is a nicer way to, an easier way to think about it, because now then you can use the same formula I've told you guys for like 5 sessions to memorize. So the formula, I'll say it one last time, is top bound n. Again, it doesn't have to be n, it can be whatever the top bound is, equals 0. Now what we're going to do is have x to the I is equal to, and this is the formula, n plus 1 minus 1 all over x minus 1. And this will give you the same answer that whoever was just talking about. So now at this point, we're going to want to solve for this, because we're going to end up plugging in n eventually. But let's just solve this portion right here. So let's plug this stuff into the formula. So our top bound is k minus 1. So we're going to have x to the power, or sorry, x is going to be whatever this is right here. So there's going to be 2 to the power of k minus 1, which is our n, plus 1 over, oh yeah, and your minus as well, don't forget that. And then over 2 minus 1. So 2 minus 1 is just 1. We don't have to write that. So we're just left with, if you think about it, k minus 1 plus 1, you can just remove that plus 1. Or you can remove the minus 1 and the plus 1. So 2 to the k minus 1, this is what he was talking about. So yeah, for those that can see it, you can just go straight to that formula. For those that might not be able to, then this is how you can think about it. And again, we have our 2 to the k here. Okay, so now we've done enough stuff. Let's solve it. Now that we have a general form down, let's look at our base case real quick. T of 1 equals 1. So, you know the drill, set what's inside T of 1. 1 is going to be what you're going to have inside, equal to what's inside here. And let's just solve for both n and k. And then we know our k is equal to log base 2 to the power of n. Okay, so that's good. Now at this point, let's just plug away. So 2 to the k equals n. We want to remove all of our k's. Let's plug in n for this. So we have n times, this just becomes a 1. So because you know you can plug in n over n is 1, t of 1 equals 1, etc. So we have n times 1. We don't need to write the times 1 plus 2 to the, we have a k here, but we know that 2 to the k is really equal to n, so we can just write n, and then we have our minus 1. So I just did a substitution from this right here for both of these, and even right here as well. And now we have 2n minus 1, and our big O is going to end up being, or I don't know if they want it in this form. They said closed or tight or something like that, but yeah, it's going to be O pretty much. So let's check our answers. Okay, so yep, that checks out. We had 2n minus 1 t of n. Yep, so that's That's how you can do it. So again, do your 3 iterations. 2 points, 2 points, 2 points. So you pretty much can, if you can do algebra, you can get 6 points. So that's good. All right, so this is the last of recurrence relation. Now let's hop into summations real quick. Just do 2 questions. Okay, this is probably the worst summation question of all time, but
That's facts.
this one is definitely the worst one.
100%. You gotta do like 4.
I did this one. It was like a whole 2 pages almost.
Mm-hmm.
Shoot, hey, time's coming up. I might not want to do this. You know what? Let's skip this one, everyone. Sorry. Just no one wants to do that. Not even I want to do it. Let's do it. Let's go over something else. Let's do this. This is easier, take less time, and people will be less confused. So, because generally the format is gonna come, it's gonna be just like these standard summation. It's not gonna be some prove whatever, So, sure, they might come up, but hey, probability over possibility. Okay, so four I plus 7. They say your final answer as a polynomial of an squared plus bn. So an squared plus bn. Okay, so let's go over this. Oh yeah, and let me also write the other one just in case I run out of time. These 2 should be very quick.
So on the formula sheet, I see that we have like some of the summation like formulas, but it also has like some of the functions from like the libraries. So are those like the only functions we're allowed to use, or?
So give me a second. Let me just go to that so everyone can see it. The formula sheet. Okay, so yeah, they have standard library, math, string, and they also have some summations. So were you asking more about the summations or about like the coding?
The coding. So like they don't have string dupe. So like any question related to like mallocing for like a word or whatever, are we not allowed to use that then?
What do you mean mallocing for a word?
So like instead of mallocing for an extra like space and null character, could I use like a string dupe?
Yeah, like
String
instead of doing like, I guess, string copy plus 1 for the null, string dupe automatically like mallocs.
Oh, I actually never heard of that. But hey, it's not here, and yeah, I wouldn't do that because that kind of defeats the purpose. Like they're trying to see, can you, like,
Yeah,
So I wouldn't pull something out like that. If it's not in here, don't use it. Just go by that. Yeah. So yeah. All right, so let's go back to this real quick. Okay, so this one, we have an expression. An expression, this is a term, this is a term. This is an expression. So what we can do, we can split up the expression into 2 summations. So what that's going to look like, when we're splitting like this, we're just going to keep the bounds the same because we don't have to subtract anything out. We're just starting from 1, and we know our summation formulas start from 1. So plus I equals 1 to n plus just 7. So okay, so let's start off with this one right here on the left. I start off with the one on the right last time, but okay, so for I, we know that our formula is going to be n I equals 1 I, right? So what can we do? Whenever we have a summation, if we have 4 times I, we know that it's going to go 4 plus 1, or 4 times 1, 4 times 2, 4 times 3, etc. So we can just pull out the common term 4. So what we can do is pull this 4 out. And now when we pull out the 4, we're just going to have this. And this we can plug into our formula. Okay, so this is I. There we go. So we have 4 times formula. So again, I'll say this like for the 40th time. This is not going to be n always. It's just going to be whatever is right here. That's what it's going to be. So remember the formula is n times n plus 1 all over 2. So with this n, it's going to be 2n times 2n plus 1 all over 2. Okay, so let's just solve this out. We have we have a 2n times this stuff, and we have divided by 2. So let's just remove this 2 real quick, but don't remove this n. Don't remove the n. So just, remove the 2's. So now we have 4 times n times 2n plus 1. So let's just do that real quick. Let's distribute this n to n plus n. And we have a 4. So we have 8n squared plus 4n. Okay, so we're good with this. Now let's go to what we have over here. So this is a common formula. I don't think it's on the formula sheet. Let's just make sure. Is there a constant formula? Okay, I don't see it. Actually, it might be
The first one.
First one, but oh, no. This is not it. This is different. Hey, actually, I don't think this is even correct. H just equals Cn. Yeah, no, that.
I think it's just CN, right? Is it not?
Oh, no. Oh, okay, so we're thinking about a different kind of formula, I think, in this one, because they pull out like Cn and then I and all that stuff. But
I think
the one
that's two
I'm
different.
No, that's for
No,
another.
That's a different. Like, go back to the formula sheet really quick. Like,
That's a
I think
second
it ends at-
summation.
Yeah, it ends at it ends at CN, and then the new summation formula they're showing you.
Oh, okay. Never mind. Okay, well, I'm talking about the constant formula. So the way I'm used to seeing it and thinking about it is
Mhm.
you have a summation, top bound, bottom bound, I equals bottom bound. Then you have C. So this is just equal. So if you guys want, write this down. Whenever you just have a constant sitting, C times B minus A plus 1. So write this down if you guys need to real quick, because I didn't see this written like this on the formula sheet. But yeah, the whole idea, I'll just run through it real quick. Yes. Yeah, let's just say this is 5 and then this is 6. If you're starting at 1, 3, 4, 5. So if you're starting at 1, you're going to want to add 6 this many times, so 5 times. So what it ends up doing, it takes B, which is 5 minus 1. So imagine you have an array, 5 minus 1, that'll give you 4, and then you have to account for the last element, because pretty much what it is, it's kind of like exclusive of 5. So you add 1, and that'll account for that last iteration, so it becomes inclusive. And then you just times it by 6. So yeah, that's kind of like how the logic works. But yeah. So that's the formula I'm going to use. So we have this constant. Our constant is 7. Then we have top bound B minus bottom bound A plus 1. Cross this out. And now we have plus 14n. We combine like terms right here and right here, and we're left with 8n squared plus 18n. So this is our final answer. Okay, so we've done this one. Let's go on to this one over here. Okay, so this one, we have an expression. Let's split it up. So let's keep our bounds the same for now. We're going to have 3i plus 100 I equals 21 of 1. Okay, so let's start on the left side again. Pull out the 3. We have a constant. Pull out the 3, right? So now we just have this summation. And for those that were here on one of the sessions, we have to sum out the prefix sum, which this is like a technique that I explained in the summations video. Go watch it if you don't get what I'm going to talk about. But pretty much you're going to split the summation and subtract what comes out before 21. So everything from 21 to 1, you're going to subtract out. So we're going to do 100. I equals 1. This is a 3. This is an I. Minus. Oh, by the way, this 3, it would apply to both. So I'm just going to multiply this whole thing by that 3. Okay. And this is also going to be I. This top bound for this right here is going to be 1 minus what was right here. So we're going to have 20 I equals 1. Again, the whole idea, if I equals 3, we're going up to 5. Easy way to get the formula. We're going to have to use some sort of formula like I equals 1. So we can do, because this really represents 3 plus 4 plus 5, we can use the regular formula starting from 1. So 1 plus 2 plus 3 plus 4 plus 5. We can end up getting 3 plus 4 plus 5 from the formula if we subtract out what comes before 3, starting from 1. So if we subtract this out, then we have what we need. So that's the whole idea. We're going to subtract out the prefix, like the sum of the prefix of it. You can think of like this 3 to 5 as a suffix. The prefix would be 1 to 2. So that's the whole idea. Okay, so now let's just finish solving this part of it. We have our formula. Our formula is just going to be same as always been. So 100. We have n times n plus 1 over 2. So 100 is n. 100 plus 1 is 101. All over 2 minus, remember we have our times 3 on the outside, minus 20 times 21 all over 2. Right? Okay, so now we're going to have to do some math. This right here is going to be equal to 10,100, yeah, divided by 2 minus 20 times 21, so that is 420 over 2. And remember, times 3, still have to deal with that. So if we just divide these things out, I'm just going to end up with 5,050 minus 210 times 3. So this should be 4840, I believe. Yes, 4840 times 3. Okay, so now let's do this. So this is going to end up being 12,000 plus 2,400 plus 120. Okay, 14,520. And now we got to remember all thing we had all the way up here. So let's just copy it down, because we've only done one side of the expression after we split up the summation. But luckily, this one's not going to be that bad. So it's actually going to be pretty simple. Plus. And right here, you could split up the summation. Honestly, you really don't have to if you think about it. Because say if you're adding 1, actually I'll just leave it as it is, but you don't have to split it up. In this case, whenever you have a constant, you can just go by the numbers, the top bound and bottom bound. You don't have to split it up, set it equal to 1, and all that stuff. Subtract out the prefix of 21, which is 1 to 20, etc. You don't have to do none of that right here. If it's a constant, you can literally just use the same formula, C times B minus 1 plus A, and be on your way. So C is 1 times B, 100, minus 21, plus 1, So minus 21 plus 1 is going to become minus 20, minus 20, or 100 minus 20 times 1 is 80. 80 plus 14,520 is 14,600. And that is our final answer. So if you have a constant, it doesn't matter if it's 1, doesn't matter if it's 10 to the 40, like it doesn't matter what it is, just use this formula and that'll do it for you. It could be 6, it could be 10, it doesn't matter. But you don't have to split this up in the whole prefix thing I was talking about. So first summation 8n squared plus 18n. Second one, we had 14,600. So let's see how we did. That's right. And this is right as well. Okay, so
Quick question. Are you guys gonna post this session?
yeah.
Where
Have
the
you
link is-
watched any of the previous ones?
I just watched the one that is public on Hack YouTube, but I haven't seen the other ones.
Okay. So have you used this website right here?
No, this is the first time I'm doing this website.
Okay. So here, I'm gonna send it in the chat. You can go to this website, and this is like the study tool that I made that you can select, your topics, specific topics, etc. And yeah, you can go right here to the comment. The moment you get on the page, you'll see it, and you can just go to this link, and it'll give you both of them. The SHPE UCF one is the most recent one that I've done. Night Hacks is the older one. I recommend you to use the SHPE one, because the Night Hacks one was my first time, and I didn't have this website, so things were moving a little slower. So yeah.
Oh, perfect. Thank you very much.
Yeah, no problem. I've done all the topics, so you can see them. And I put in the video, you can see like what sections I've done. So let me just show you real quick. For example, recurrence relation. So right here, algorithm analysis, space conversion, recurrence relation, etc. So okay, so let's go to the next question. So we're just going to do one more real quick. Oh boy. Okay, let's just do
Another long one.
Yeah. Hey, I'll do it. This is that's up.
Yeah, that's a pretty long one as well.
Yeah. Hey, but I'll do it. Okay, if by the way, guys, if you can get this, you can get any question on summation, trust me. Okay, so and when you guys see the solution, so I'll explain the solution that they gave, and I'll also explain the solution that 99.9% of people are going to do. So let's just write this down. So they give you this summation. So they give it to you as n squared plus n minus 4, I equals n squared minus 3, I plus 4. Okay. And by the way, they want our form in a format such as this. This is a B. My B's look like 6s, but there we go. So this is going to be final form. Try rewriting the summation into an equivalent form that generates less algebra. So by the way, that's easier said than done, but let's just go through all the algebra real quick. Let's go through all the algebra, and then I'll explain the easy version. Okay, so we're going to go the hard way, and then I will explain the easy way. So first things first, we have an expression. Let's split the summation. I plus, yeah, I'm giving up on these on my notations. It just looks worse and worse every time I draw it. But 4. Okay, so now let's just deal with this right here. We're gonna have to do the whole prefix sum removal thing that I've been talking about. So let's have some big brackets because we're gonna need them. So we're adding a sum. Remember, our formula always starts at 1, goes to 2, 1 plus 2, etc. And in this case, we're going to hit n squared minus 3 sometime. And then the last term is going to be n squared plus n minus 4. So again, to get this sum, which is what this is asking for, we're going to have to subtract out this whole region before, the prefix sum subtraction. So we're going to write it all in terms of, starting from 1, 4i. But guess what? We don't have to do that. So yeah, exactly. I'm about to mention that. So you don't have to do that right here because I explained it before. So that's a good catch. Since this is a constant, it doesn't matter what your top and bottom bounds are. You will get the right answer no matter what. So we can just do C B minus A plus 1. And that's it. We're done with that. We don't have to split. We don't have to do this. We don't have to do that. Because if not, we have to split into 2 summations, plug the formula in for both, do the discussion in algebra, and all that stuff. But since this is not I, in this one, we're going to do that. But in this one right here, as a constant, we don't have to. So 4 times n squared. So this is B. So this whole thing right here is B. Plus n minus 4 minus A n squared minus 3. But remember, your parentheses, always put your parentheses. If not, you're going to mess up, because then you're going to do minus n squared and then, forget minus on this. So let's solve the inside first. So we're going to have n squared plus n minus 4 minus n squared plus 3, right? So let's break out like terms, just remove them. This is done. This right here is also done. So we're going to end up with negative 4 plus 3. That's going to give us negative 1. So we have 4n minus 1. Oh, and the plus 1. Yeah. There we go. Plus 1. My bad. Forgot about that. You see, it gets very tricky with this one because, there's a lot of stuff to write out and remember. So, yeah, the plus 1 exists. So with that plus 1, we actually go to negative 4 plus 4. And that's just 0. So we just have a 4n right here. So these cross out, this cross out. And 4n, yeah, so we just have a 4n. Now let's deal with this other stuff over here. So okay, so we have to start insert in terms of 1, I, and now we're going to do the prefix sum subtraction. So take this minus 1 minus 4, I equals 1, and I. Okay, so now let's go. So formula, n squared plus n minus 4 times n squared plus n minus 4 plus 1. So let's just cut this off right here. This is going to be minus 3 because of the plus 1. All over 2. Amazing. So now let's just set this up real quick. N squared minus 4 times n squared minus 4 plus 1, meaning minus 3. Oh wait, yeah, okay, so that is good. All over 2. So again, let's just put all of this all over 2. All right, so let's deal with this right here. This is definitely the worst part. So we're just going to distribute everything. I'm going to start at n squared, do all this, same thing for this, etc. So let's just do it. Start all the way over here, make sure I got enough space. So I'm going to have, and by the way, I'm going to do these two terms, and then we'll solve from there. So we're going to have from this first region right here, n squared plus n to the 3 minus 3 to the n. Now we're on this term plus n to the 3. Okay, so let's just make sure n squared. Yeah. Okay, so we're all good so far. Then now we're going to have plus n squared minus 3n minus 4n squared minus 4n plus 12. Okay, so that's 1. We still have this over 2 that we're dealing with, so. Okay. Minus, now this is going to be easier, so n to the 4, then we're going to have, is it 3n squared minus 4n squared plus 12. Okay, and if you notice, we have a minus, so we must distribute. So what I'm going to do, so I don't have to rewrite this like a million times, we're just going to distribute it right now so we don't have to deal with it. So this is a minus, this becomes a plus, and then this right here becomes a minus. And that means that now we can just remove all of this stuff. Let's put our minus back. And we can deal with all of this disgusting stuff all at once. Okay. So, by the way, guys, I'm just saying right now, I may have messed up because this is horrible. This is a bunch of stuff to deal with. So, don't be surprised if I might have messed up a term somewhere. But n squared, n squared. So these two are out. Or sorry, n to the 4th. Then, huh? What's up?
I think you did it right so far. That's what I have.
Okay, cool. So
Same,
this
I
is
have
out the
same
door.
so far.
Now, let's see, we have a 4n. So yeah, I'm just going back and forth, seeing what they have in common. So, okay, we can scratch out 4n squared. We can scratch out this 12. And that leaves us with everything that's left. So let's just group like terms. 2n to the 3 plus n squared minus, and then we have, looks like we have a minus 7. Okay, yeah, minus 7n. Okay, and this is all over 2, so don't forget that. All over 2. So I'm just gonna delete this right here. Minus 7n. I don't know where my n went, but let's just write this all down here. 7n. Okay. Now we have this all over 2. And remember, we have this 4 on the outside that we've just not touched for a long time. Okay, I just deleted it. There we go. So let's just divide by 2. So if we divide by 2 on this right here, it'll give us this. Okay. Yeah, so we're just dividing these, and then these. So it's going to give us n to the 3 plus, if you divide something like just over itself, this has a 1 over 1. So divide that by 2 is just 1/2 n squared. Then we have minus 7 over 2 n, right? And now we have a plus 4n. So we have a bunch of terms in terms of 1/2, and it's easier to turn this into a 1/2. So 4 over 1 times 2 to the 2. Now we have it in terms of denominator 2. So now we're going to have 8 over 2. And if we do this math, we're going to end up with n to the 3 plus 1/2 n squared. We're going to have a negative 7 plus 8. You can think of it like that. So now we're going to have a 1 at the top, plus sign, 1 over 2n. So this is our final answer after all of that. So we save some time because right here we recognize, okay, it's a constant. There's no I, there's no whatever. So yeah, there's no I. So we can just take the bounds right there. No need to split. So Please do not sum out the prefix on this because it will take you forever. Remember, you got 10 minutes. I know it's probably been a little more than 10 minutes, but this will save you. But now we've gone to answer, and I know for sure this is the right answer on this question because, it's not my first time doing this one. But now let's go on to the different explanation as to why it can be so short, because their solution is like 3, 4, 5 lines max. It's not none of this. They don't even split it at all, I believe. Okay, so let's take this original summation and let's analyze it a little bit. Let's see what type of information we can get from it. So I believe this technique is called index shifting, but honestly, if you don't get what I'm going to explain right now, it's fine because these questions almost never come up. I think this is the only one that I've seen where you can do a trick like this, but honestly, I wouldn't worry about it. You can get by with just regular splitting, prefix sum, subtraction, all that sort of stuff. So, okay. So let's think about what is going on every iteration of this summation. So we're going to start with n squared minus I. So this is going to be our first term. So I'm just going to write out what the first term, second term, third term, etc. is going to be. So we know that this is going to be a table for I, and this is just going to be like whatever comes after. So we're going to have a +4 for all of these, right? And then we're going to have, let's just have result. So we can best explain it. Let's call this expression. Rest of the expression. Okay, so let's do the first couple terms. Remember, we're going to be incrementing I so it can approach the top bound, right? So we're going to keep incrementing this until we approach the top bound, and then we just hit it, and then we're done. We do that last iteration. But this means that we're going to add 1 because, again, n squared plus n minus 4 is greater than n squared minus 3, so we have to go up. So going up entails adding 1, since we have to go every step. So -3 plus 1 is going to be -2. Then let's just go another step and let's see what happens. N squared minus 2 plus 1 is going to be -1. N squared minus 1 plus 1 is just n squared. Then we're going to do n squared plus 1, because this is really just +0. N squared plus 1. And I think you guys see what's going on. We're just going +1 plus 1 plus 1 based on n squared. So if you notice, there's only one thing really changing, which is going to be this right here. But we'll see how that can play in as of right now. So if we do +4, remember we still have this +4 as part of the expression because our thing is I plus 4. And we have this right here from I. So this is I, this is the rest of the expression +4. So let's just apply this +4 to every term. And you guys might start to see something because notice this term right here, it starts at -3. It doesn't start at +1. It doesn't start at any sort of thing that we can start off based on off of a regular summation that goes from 1 equals or I equals 1 at the start. So we can't plug it into formula just yet. So let's apply the full term. So it's going to be n squared minus 3 plus 4 is +1. Minus 2 plus 4 is going to be n squared plus 2. Minus 3 plus 4, n squared plus 3. And yeah, let's just do these last two. So n squared minus +0 plus 4. N squared plus 1 plus 5. That's going to be n squared plus 5. So as we notice, the first iteration, we have a +1. Second +2. Third +3. 4 and 5. So this is running on the same type of logic as a regular summation that we're used to, like the whole n times n plus 1 all over 2. So this is the whole way it's running. So if at every iteration we go from 1 to 2 to 3 to 4, that means that and notice how n squared is a term in every single one. N squared is a constant. And really what our summation looks like, instead of thinking about it like this, we can rewrite the summation to actually be equal. And let's just write it right here. This right here is actually equal to I equals 1 up until, and let me see. So how can we determine the top bound? Let's just plug in the last term, which is, remember, summations are inclusive. Let's plug this in to right here and see what our last term is going to be. So if we do, let's go right here, dot, 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 eventually you'll get there. N squared, I believe it was, what was it, plus n minus 4. So there's our I. Then we do plus 4. We're going to end up with n squared plus n. So that means that the last one we're going to end up running up until is going to be eventually, so after we do all of our iterations, n squared plus n. And of course, n squared is a constant through all of these iterations. So we're going to be ending on n. So we go from 1 to n. So it's a very common format that we're used to. So we know that our constant is n squared because it always appears, and it's not like based on I or anything. So we're going to have n squared plus, we start, if I is going to start at 1, 1, 2, 3, this means that this term is going to be I. So I, and now from here, what is the last term we're going to add in? The last term we're going to add in, we figured it out from this right here, which is going to be n. So that means the top bound is going to be n. So we're running from 1 to n squared plus I, starting at 1, ending at n. So does that check out? It does check out. And now from here, we can just take this whole thing and split it up, right? So let's just split it up. And we're going to end up with something like this. I equals 1 plus. And okay, so now we're right here. Now let's think about it. Let's think about coding a little bit, right? So whenever you have a for loop, because that's really what a summation is. A summation is just for, and you go I equals 1, and then I less than or equal to n, etc. plus 1, I plus plus. So if we think about a for loop, our n, in most cases, when you have a for loop, you're not running infinite for loop, meaning this n has to be a fixed value. Normally, what do you do? You use a function, so f, and then you pass in, let's say, for example, an array, and then you pass in an n. So your n is fixed either here or it's inside your function, int, n, etc. So n is going to be some sort of fixed value that you're going to be running up until, or you might be using to, stop your iteration. It's not going to be infinite when it comes to a for loop, unless you got a while true, etc. But in this case, it's going to be running up until n. That means that n has to be something finite. It has to be some number that we can reach, meaning that this number is a constant. It will not change. Whenever you do a for loop, for the most part, you're not doing, up until n plus whatever, and it's going to be changing as you go through the function. Most of the time, it's just going to be, okay, I'm going to go from this number up until n, or I might go from n down to this number, etc. So n is a constant, because if not, then you're never going to end. Then at that point, you might just have an infinite right here. So n is a constant. By n being a constant, you can bring it out of the summation. So we can have n squared and I equals 1, and this is going to become 1. So, if you knew it was a constant, you could plug it into the same formula, the c b minus a plus 1. I just wanted to explain why it's a constant, because this has to end somewhere in this case, right? It's not infinite. So this is what we're working with right now. And now from here, we have a common formula. So this is a constant summation. So now we have n squared. So this is n squared times the whole thing. So it's going to be, constant is 1. So 1 times n, which is b minus a, 1 plus 1. And this is just going to cross out. So we have n squared times 1 times n, which is just n to the 3, right? Then now we're going to have plus this term right here. And this is the perfect example of a formula. We just plug it in. So n times n plus 1 all over 2. And right here, this is n to the 3 plus, let's distribute this out, n squared plus n all over 2. And this will give you what we got earlier. If you just, break it up, 1/2 n squared plus 1/2 n. And that is how you end up with the same answer. Supposedly, I guess in less steps, or not supposedly, it is in less steps, but you have to notice this type of thing. I'm not recommending you guys to understand or like try to implement, because this is probably not going to come up. It could, but as you saw, you can do it this way. And really, if we think about how hard what we did was, this was just a constant. We just used a formula. You just have to remember and do good algebra. As long as you do the algebra, you can easily solve this. The hardest part, of course, was this right here, because this, you make one error, there goes your whole thing. But they're designed in such a way that you can subtract things out. Like you guys saw, I subtracted a bunch of things out, 4 or 5 terms, and then I simplified it. So it wasn't necessarily that bad. We only really have to do one thing that was kind of hard. This part was pretty easy. But yeah, those are some tips to speed it up. If you see a constant, doesn't matter when it's starting and ending at, just plug everything in. That's it. You don't have to split it or do the prefix subtraction, etc. So this is how they ended up coming with this. Okay, so yeah, so look at their solution. Yeah, don't feel bad if you didn't get this one, because most people did it. I'm 99% sure. Okay, so does anyone have any question on that one? Okay, so let's go on to the next. So we just did 2. That one was pretty long, but let me see what the rest of the topics were. Okay, so people wanted bitwise, then they wanted tries. So let's do some bitwise real quick. There we go. Okay. So which type of bitwise questions do you guys want? Do you guys want some of the word problem, or do you guys prefer the ones that are like just calculating numbers, applying like or, and, XOR, etc.?
Word problems.
Word problem. Okay, cool. So I'll give you guys like a minute or 2 to work on this one. So yeah, when it hits 8 o'clock or 8 on this timer. Just give me 1 second. Okay, so all right. So this question, they say there's a total of 25 cards, numbers 0 through 24. We can represent a set of cards with a single integer by setting the ith bit to 1 if the set contains card I, and setting the bit otherwise to 0 otherwise. For example, the set of cards 2, 6, 7 would be stored as the integer 196. So 2 to the 7 plus 2 to the 6 plus 2 to the 2. Okay. If the set of cards is disjoint, if and only if no card appears in both sets, complete the function below so that it returns 1 if they are disjoint. Okay, so let's think about what disjoint means. It's pretty much saying, let's say, again, I said this before, but for those that have taken discrete, this will make sense. But you don't need discrete. Let's say you have a circle, right? Or a Venn diagram. Pretty much, if it's disjoint, you have something like, for example, colors and cars, right? So we have blue. Okay, so let's say we have like a red car, and let's say we have like a blue car. So I guess you can say, actually, this is a bad example. Hold on. Let me get a better example. Let's just simplify it. So let's say this is one group of things A, this is one group of things B, right? So in A, you can have, for example, 1, 2, 3, And in B, you can have 4, 5, 6. Right now, this is disjoint because there is nothing in the intersection, meaning they have nothing in common. So if we had something like 4, let's say the Venn diagrams, it was a little separated. So let's say we had 4 and 4 and with 5. These two, A and B, they have a common term, meaning what they really look like, they have an intersection. So this A and B has 5 in it. So if it's disjoint, they have nothing intersected. Meanwhile, if they are joint, they have something in there. So pretty much what you're trying to do is see if they have no intersection. And another way to see another way to say, I just said it, but intersection is really what they have in common. So just by thinking what they have in common, and also they showed it and mentioned it in the question. So I believe they said in common. I don't know if it said it, but they might have said it through different words. So it's included in both sets. It means that it's not disjoint. Meanwhile, if they have, oh yeah, right here, no common. There is no common value in the two sets. So whenever you see common, just know you got to use AND operator. Just right there, you 99% of the time. They're not going to take common when it comes to OR. They're not going to say common. Maybe when it comes to XOR, maybe, but they'll probably say like not common. But when it comes to common, 99% of the time it's AND. So if you want to see if they have an intersection, think about bitwise when you do AND. So if you have something like this, and you take the AND, you want to see what they have in common. They only have in common, remember, it's based on the ones always. So this would be 1, they both have ones. They don't have both have ones, they don't both have ones, so 0, 0. So that ends up just becoming this number binary right here. So now what we know is these term right here, this bit is common to both of them. So pretty much what they're saying is if they're disjoint, they have no intersection. So let's think about it. If they have an intersection, it doesn't matter where it is. It can be there's 32 bits in a number. So it could be at the 31st index bit. It could be at the first. It could be at the second, third, fourth. If they have anything in common, it's going to be equal to not 0. Because think about it. Let's say we have something like this, right? Let's just add a bunch of zeros. So probably not keeping track well, but let's say we have a bunch of zeros. If we take the AND of this, we clearly see they have nothing in common. If we take the AND, it's just all going to be 0, which signifies, okay, they have nothing in common. Meanwhile, if they had this, for example, or sorry, right here, this was not a 0, this was a 1, then they would have a 1 right here. They have a 1 in common. It doesn't matter where it is. Let's say they have multiple things in common. Then this right here would end up being a 1, right? So it's not equal to 0. Whenever they have no intersection, the number is equal to 0. So just by knowing that, we can come up with the answer real quick. So pretty much what it's going to end up being is we're going to have disjoint, and pretty much all we have to do, since we're basing it off of intersection, meaning what they have in common, meaning and, we can just return, and we're going to take the intersection, take the and of set 1 and set 2, right? So if they're disjoint, remember, they have no terms, no bits on. If there's no bits on, it's equal to 0. So we can just say equals 0. And that is all you have to do. That is a simplest solution. So another way to rewrite this, if this is equal to 0, you can end up negating it. And remember, if you negate a false, you end up with a true. Meanwhile, if you negate a true, meaning it's not equal to 0, the only way you can get a false when it comes to numbers if it's equal to 0. So if it's not equal to 0, it can be 1, it can be 256, it can be 3000, etc. it's going to be true. And if you negate a true, you will end up with false. So it works out in all cases. So that's pretty much the answer to this one. Set 1 and set 2 equals 0. So yeah, they ended up writing it a different way, but same thing, same difference. And this way they did it, this also works. So you can iterate through all the bits and check, do they have anything in common? So that's kind of the way that they ended up doing it in here. Personally, I would have done it a little differently, but I can see why they did it this way. What they end up doing, they end up cutting bits off by right shifting it, and they're pretty much checking, okay, and 1. If you do and 1, then it'll tell you, okay, is the last bit before I cut off shifting to the right more? Is that on? And if you do and with the next bit on the other set, it'll say, okay, are both of these bits at the end on? Okay, if they're not on, keep going. If they are both on, that means they have an intersection and therefore return 0, meaning they're not disjoint, they're joint. So that's the whole idea. It's kind of like theoretical kind of question, but again, you see common, it's either and or it's XOR. So yeah, there we go. Okay, so let's just hop straight into this one. In the game of NIM, there are several piles with stones, and 2 players alternate taking 1 or more stones from a single pile until there are no stones left. The person who takes the last stone wins. It turns out, if it's someone's turn, if they play optimally, they can win as long as the bitwise XOR of all the numbers of stones in each pile is not equal to 0. Write a function that takes an array of values representing the number of stones in the pile of NIM and the length of the array, and returns 1 if the current player can win, otherwise 0. Okay, so that's all. It's a whole lot of BS. There's a lot of stuff you don't have to care about. So this is one of those questions that it's 10 points, but it's one of those where it's kind of like a freebie. So it says they can win as long as, and they literally tell you what you do, the bitwise XOR of all of the number of stones in each pile is not equal to 0. So just a quick little recap. What is XOR? XOR, as I explained it before, is kind of the opposite of AND. So we know AND. Okay, this is a bad example. So AND, what it does, the way I explained it before was, imagine there's someone you want to speak to. You want to see what you have in common with them. If you have something in common, they will like to talk to you about that. So just take that, and everything you don't line up with, you don't take those. So 1 0, 0 and 1, etc. 0 and 0 also counts as not lining up. So they only you only take the values where you're both on the same page. So AND is kind of, you can say nice, right? In that sense. Meanwhile, XORs mean it likes to argue, meaning in this case, what's going to end up happening, and also let's just add a 0 0 just so for explanation. So the way XOR works, it's doesn't want to talk to you based on what both of you like. It actually likes to argue with you, so it's mean. So wherever you have anything in common, meaning if 1 1, you either have something in common or you have nothing in common, or neither of you have it. Like right here, these are both going to be equal to 0. But wherever there's a disagreement, that's going to be equal to 1. So 1 1, that's 0. 0 0, that's also 0. But there's a disagreement at 1 0 or 0 1. So what's going to end up happening is these two are just going to be 1. So notice the clear difference between XOR and AND. This is it right here. That's explanation of XOR and AND. So think about it. If you have any number that is not 0, so if you have a number, let's say any number that's not 0, and you XOR it with 0, what's going to end up happening? it's literally going to be the number itself that you XOR 0 with. Because it doesn't matter what this is. It doesn't even matter if it's 0, 0, 0 and XOR 0, 0, 0. It's still just going to end up being 0, 0, 0. So in this case, and of course, you can flip it. So this right here would also give you the same thing. 1, 1, 0. This will give you 1, 1, 0. So XORing something against 0 would just give you the number itself at that start, before you start XORing on top of it. So what they're telling you, literally telling you everything you have to do. You take the bitwise XOR of all the numbers, and from there, you just return whether or not that equals 0. So what that looks like, let me just zoom in real quick. It's just going to look like this. So we're going to have one number. So let's call this answer. Set equal to 0. And now let's iterate. And I use X. So sorry, guys. And I'll do my plus before. So now right here, all you're going to have to do is take every pile of stones, which is, the current index you're at, and you're going to XOR answer because it starts off at 0. So the first value it's going to take is going to be piles of 0. So the first XOR is just going to be piles of 0, and then you're going to compound those XORs, like piles of 0 XOR piles of 1. Piles of 0 XOR piles of 1. Let's XOR with piles of 2, piles of 2, and so on. So really, at the end of this, you're just going to end up returning answer. And not answer. You have to check if it's not equal to 0. So after you take the bitwise XOR of all the number of stones in each pile, if it's not equal to 0, then somebody can win the game playing optimally or whatever. So return answer is not equal to 0. And that is literally it. That's 10-point question right there. So a lot of these, not necessarily this one, but more like the disjoint, a lot of these bitwise questions, they tend to be more, how could I say, they're more creative in a sense, even though in this one, they literally tell you what to do. And there's certain things you can pick up on this, but yeah, this is all you got to do for this one. So 0 XOR not equal 0. That's it. So I want to cover one last bitwise. I think I've already done 2, but let me cover the fence. Okay, this is also a very good one to do. Does anyone want to see the fence question explanation? Or I'm sure you guys have probably heard of it. It's the one. Okay, the fence. Okay, then well, I will skip this one. And I will go to the fence. There we go, the fence. Okay, so I'm just gonna go line by line because this is actually the foundation that I took. So I know where like the whole thing that gives away the whole question is that, because it's a lot of writing, a lot of BS. You don't really need all this, but so imagine the task of painting a picket fence with 20 pickets. Okay, 20 pickets. Let each picket be numbered from 0 to 19. That makes sense because 20 pickets, 20 bits goes from bit 0 to bit 19. From left to right, initially painted white. Okay, so let's notice. The pickets are each initially painted white. So that means they all have the same color. So that's going to be relevant. So let's just write this down. All pickets, same color. Okay. A pattern is 5 picket long and can be placed with the pattern's left aligned with any picket between number 0 and 15 inclusive. So pretty much a pattern is going to be something, and we know we're using bitwise operators, so it's going to be something that looks like, let's say, this right here. So this is 5 bits long. So this is like a pattern that you're going to place on 5 pickets because that's how long the pattern is. Okay, so the left end aligned with any picket, okay. And let's see. So it says if you line up the pattern with any of the pickets from 16 through 19, the right end goes past. The right end of the pattern goes past the right end of the fence, and this isn't allowed. Picture is below of an example pattern with 3 of 5 possible pickets painted. Okay, painted. So if this pattern was lined up with picket 4, then pickets 4, 5, and 7 would get painted. So let's think about that. Let's write out the bits that we can have. So we're going to have, for example, 0. Okay, so we picket 4. So let's see. So this number right here, this is just 11. So pattern is just equal to 1, 1, 0, 1, 0. So yeah, so this is 2. Actually, this is not 11. Okay. There we go. So this is 1, 4, 8. Wait a minute, what's going on? Oh, there we go. My bad. Yeah, I just blanked out. My bad. Okay, so 2, 2, 0, 2, 1, and 2, 3. Okay, so this is the pattern that we're working with pretty much. Oh yeah. The whole reason I got it wrong was because you're thinking about it in flipped. So these 2 pickets are on this side, and then the 1 is right here. So that's why I was like messing up. But yeah, they have it right here. So if we place this on picket 4, 4, 5, and 7 would be painted. So let's say we place it on 4. That means that, remember, bits go from right to left, not left to right like an array that we're used to. So this means that this is 4. That means that this right here would be 5. And then we would have, let me just write 7 and 6. That's easy. So this is the pickets and how they align right here. Okay, so these are the pickets. So 4, 5, and 7 are aligned, or they're painted. One way to paint the fence is to line up the pattern with a few different picket numbers and apply the pattern. For example, and this is the part of the question that gives it away. And it's very subtle. You have to go deep into, all this story and all this stuff, explanation. For example, if we lined up this pattern with picket positions at 1, 4, then the pickets would be painted would be 1, 2, 4, and 5. Okay, so this is the part that matters. Notice that painting an individual picket more than once still leaves it painted. So that is very subtle, but that gives away the whole question. So what type of, we're dealing with Bitwise, right? So what type of operator can we use such that when we apply it, if something was already there, then we can keep that kind of status. Like it's not going to go away. So let's think about what we have. So we have left shift, right shift. Then we have XOR. We also have AND. We have OR. Yeah, and I think that's about it for what we use here. So left shift. Does left shift leave the same value? Like if you already have it? No, it doesn't. It just shifts everything. Right shift doesn't do that either. So we can throw those 2 out. Those cut out values, they don't like persist values, if that makes sense. Like it's not going to keep it there. It's going to shift it over, and it may be there unless it gets cut off or whatever. But XOR, think about it. If something is painted, we can think about painting as a 1 or a 0, right? So let's just say, remember, everything is colored white. Let's just say, yeah, exactly. It's bitwise order. So let's just say white is 0, and let's just say black is 1, right? So what's going to end up happening is if you have an XOR and both things are painted, like the pattern and where you're going to paint, let's say you have something like this, then wherever it was painted the same, meaning this right here, in XOR, it's going to turn both of them off. And it's actually going to become, actually, we need to XOR. It will just end up becoming 1, 0, 1, right? So wherever it was already painted, it's going to, leave it there. Or sorry, it's going to remove it. Meanwhile, and I'll just go through the rest real quick. It won't take too long. When it comes to AND, it'll only keep places painted where you know, it was already there. So 1, 0, 1, right? But the whole difference, because here it looks like, okay, let's say this is the fence, right? And like, let's say this is the pattern. So right here, if we could apply and, it seems like it checks out, oh, it might be and. But the thing is, what if you line up your pattern in such a way that, like, how can I say this? You line up in such a way that it may not have been painted before. So let me just come up with an example real quick so you guys can see what I'm saying. So let's say you have a pattern, it's 5 digits long. So this is your fence and this is your pattern. So if we apply and right here, and let's just say this is our pattern, it's just 0, because remember, it's only 5 digits long, meaning everything after this will just end up becoming 0. So if we apply the and on this, we're actually going to lose out on stuff that we had previously painted, which directly violates, notice that painting an individual picket more than once still leaves it painted. Here, you're not painting it twice, but you're actually, by doing and, you're actually losing what you painted. So it's like you didn't even paint it, which violates it. Once it's painted, you know, you can tell if it's painted or whatever in terms of like the problem, I guess. So this will end up giving you this, which is really not what you want. Also, and let's say you had a different type of pattern. This would, again, destroy what your fence is. So now you would say, oh, this is my fence, but this is not your fence. You already painted. There's 2 pickets that got removed. And that's why you use or in this case. When it comes to or, it doesn't matter if it was painted, if, you know, the things line up, etc. So like right here, if we take the or of these two, we know that this picket was previously painted, meaning there's going to be a 1. This picket was also previously painted, it was going to be a 1. And also, let's just add 1 randomly. These pickets also painted, You painted over them again, but since they were painted, they just stay painted. You just like leave them because you just care if they've been painted or you will paint them. And here, this one would also have, like, if this is the pattern, for example, I know they're only 5 digits or bits long, but for an example's sake, let's say this one was also on, then this would also be a 1 right here. So the whole idea is, this is why you don't use and, because if not, you're going to lose things that you like painted over based on wherever like you shift your stuff around to. So you will only ever really have like one kind of like pattern, really, if you think about it with and, but that's kind of irrelevant right here. You would only be able to place it once and kind of and like keep it the same. But yeah. Oh, and actually, one thing I just want to mention: if this is just assuming the fence has been painted at some point, but just think about it. If the fence starts off empty, like completely empty, it's just all white, but you want to paint it like some other color, right? Let's say this is your fence, and let's say this right here is going to be your pattern. If you take the and with this, you're never going to paint your fence. You know that completely destroys the whole purpose. Because if you take and, it's just going to be, okay, an empty fence, all zeros, and something that may or may not just be 0. You're never going to get anything. So your fence is really never getting painted. It just has the, it's just completely unpainted. So that's the whole idea behind or. So we're going to have these locations in this array of where we can shift these patterns, or like the main pattern. So we're going to be shifting over the pattern. So we might, for example, we might apply this pattern. We might apply it right here. We might apply it right here. We might apply it right here. And we want it to have the same OR behavior. But the paint location is going to tell us how far. So right here, this is paint location of 0. Meanwhile, this is a paint location of 2, etc. And this is a paint location of 0, 1, 2, 3, 4, 5, and 6. So that's the whole idea of this. So let me just expand this right here so the answer doesn't come up. So we're gonna have our fence. We're gonna say it's unpainted, right? So this can just be fence equals 0, right? And from this point on, we're gonna go through all of the possible paint locations that we can place it in. So let's just do paint length. So it's gonna be the length of possible locations we can apply this pattern onto. Right, and right here, we're gonna end up doing this part. It might be a little tricky. Remember, we're taking a pattern and we're applying it over a certain range of bits. What is the range? The range is gonna be, let's say we have paint locations. It's an array of something like this. What's gonna end up happening? You're gonna shift it this many times to this bit and see where you can place it, right? Or pretty much you're gonna OR it into place. So we're gonna have our fence, which is what we're painting. And here I'm going to do OR equals. I'm just going to say, okay, fence, OR it, and then set fence equal to the result of the current fence or whatever is on the right side. So right here, we're going to have the pattern, and we're going to shift the pattern wherever it is. We're going to end up placing that pattern based on whatever the paint location is. So again, if we want to place it at bit 4, or sorry, at bit 3, 0, 1, 2, 3. Okay, so now right here, we're gonna apply a pattern on like in these locations. So give me 1 sec. It's gonna be right here. So we're gonna 0, 1, 2, 3. Actually, I gotta go +1. We're gonna apply the 5 length pattern on these bits right here. So it doesn't matter what it is, it'll just apply it right there. Let's say you go to 0, then that means we're going to apply it on these 5 bits, etc. So that's the whole idea. And by the way, you don't have to do any handling on if it goes past, because remember there was something that says like, oh, if it goes past the 15th bit, it's not going to be valid, whatever. The whole idea is that in this question, you're focusing on 20 bits. So let's say we have 20 bits, right? I don't know how long this is, but let's just say it's 20. If you have something and you apply it, for example, on this bit right here. So let's say this bit right here, let's just say, for example, this is bit 19, and this right here is bit 0. So 0 to 19, this is the 20 bits. So let's say you apply something at this location, which is going to be 17, right? Since this is 19, 18, 17. If you apply it right here, there's going to be 2 locations where it's going to go past 19, and according to them, it's invalid. What they mean that it's invalid is it's going to drop off. So, because really, you're not looking at the full number, at the full picture. You're really just looking at this point right here. You're really just looking at these bits. So this is what you care about. You don't care about if there's like, for example, like a bunch of ones. As long as your 19 is like this range right here is good, then you don't care what's. Yeah, and this is not going to be a 1 or 3, but you get the idea. You don't care what's past that, even if it goes past the paint location, because you're only focusing on the first 20. The first 20 are going to represent the fence. You could care less about the other 12 or 11. Yeah, so that's the whole idea behind this. So this is, oh yeah, and also you have to return the fence as well. Return the fence. And that is about it.
Wait,
So let's.
Can I ask a question?
Yeah, go for it.
Sorry, I'm a little confused on the fence or equals pattern shift left paint. Like, what is happening at that line of code? Because it kind of confused me a little bit where everything's going. Like, in each iteration is fence like increasing by the and. So,
There's no okay. So first of all, there's no and. It's
I meant or. Sorry.
Okay.
I meant or.
So right here, fence, pretty much what it's doing is reassigning fence. So now we're going to say, okay, we're going to OR fence with what the current pattern is if we shift it to a certain location. So for example, if I were to rewrite it, it would just look like this. I just cut down a step real quick, but this is the whole idea. We're going to take the current fence. So let's say this is our fence. And the example that I was saying, let's say this is our pattern.
Oh, fence is already the painted fence. What it is.
Yeah. So it's going to start off at 0. But as you apply it, of course, like it's gonna go like 1, then 1, or whatever. And,
Yeah.
and let's say this is your pattern. If you apply it again, so we just applied it to the location 0, 1, 2, 3. If we apply it at location 0, so our pattern based off what I just made, our pattern looks like this, right? So if we apply it at location 0, that means that we're gonna take the OR of the first 5 bits with this. So now it's gonna become, this is our new fence, 0, 1, 0, 0, 1, 1. And then we have a 0 and a 0, so OR will not do anything. And we have a 1 and a 1. So this is our new fence, but our fence is constantly changing. At the start, we had nothing. Then we ended up with this. Then we applied it to location 0, and now we ended up with this.
So is the pattern the same each time?
The pattern is the same. Where you apply the pattern is what changes. That'll change overall with the
Yeah.
fences.
So how comes we do it till the, because wouldn't that, so is the pattern going to be 5 bits like that?
Yeah. The pattern is going to be 5 bits, but they give you the locations of where they're going to place the patterns, which is what you're doing here. You're taking the pattern and you're applying it from range. Let's say they give you location of index 4, right? If you think about it, the pattern is 5, so you're going to do 4, 5, 6, 7, 8 are going to be covered. So from 4 to 8 inclusive, those are the bits that are going to be painted right there. Then if you do the next one at 7, that's going to be 7, 8, 9, 10, 11, and that's all 5 inclusive.
Wouldn't you eventually at like 16 be over the amount of
that's if you shift it past 16, but I'm pretty sure like they're not going to tell you here that they're not really telling you like, oh, there's a possibility of you shifting past the what do you call it, the 16 or 19, because then it would cut off. And by the way, I just explained the whole logic behind that. Let's say you applied something right here.
Mm-hmm.
These 3 bits would be out of the scope of 0 to 19, right?
Oh,
but the
yeah,
whole
so
thing is
whatever.
you only care about 0 to 19 because
Mhm.
think about what the fence is represented by. The fence is represented by 0 to 19 inclusive, meaning even if you shift past it, sure, the number is going to be different, but when you go to analyze those first 20 bits, that's
Yeah.
all you care about.
That's all you're gonna see.
Exactly. So
Yeah, that makes
that's like
sense.
the whole thing.
Okay, that's where I was a little bit confused. Thank you for clearing that up.
Yeah, no problem. Okay, so next thing, we're gonna do a couple tries, 1 or 2 real quick, and then after that, looks like recursive coding, and I think after that, that might be all I can do because I have to go pick someone from the airport a little bit, but okay. So this question is it's going to take a long time. I don't have that much time, so I'm just going to skip past this one. We'll just go to a different one. Okay, this is a good question to go. So I'll let you guys read it, try it out, and I will be back. So go for it at 7:30. Okay, so write a recursive function that takes a root, try, and a single character alpha and returns the number of strings in the try that contain that letter. You may assume letter is a valid lowercase alphabetic character A through Z. Note that we are not simply counting how many times a particular letter appears in the try. For example, if the try contains the strings apple, avocado, and persimmon, and the function calls to return P equals 2 and M equals 1. So let's see where they get that. So first, let's just draw this try out. Let's visualize it. Because we're trying to count how many strings have a certain letter. Okay, so give me 1 second. Okay, so this is the try, the root, the very, very root. So this is extension for A, P, E, L. Okay, I forgot a letter. And E. This is for the persimmon word, P-E-R, permison, whatever it was. This is for avocado. I'm not going to draw the whole thing, but you get the whole idea. I'm going to draw a triangle just to represent like a subtree. And there's going to be one for A, right? This one's going to be for an M, but etc. So let's see what the struct has for us. The struct has num words, a flag, and the children. Okay, so we know the children. We have them out here. We need the flag. So the flag is just going to tell us where there's a word. So for example, we're going to have a 1 right here at the flag, and we're going to have how many words are in this subtree. So the subtree is really everything, including and under as a child, or as a descendant is what the term is, E itself. So right here, if we have a word, and the number of words is going to be 1 because including itself in the subtree, there's only one word right here. Now, avocado. So, you know what? It's actually a better idea to just draw it out. So it makes more sense. So D, and then we have an O. Right here, we're going to have a 1 and a 1 again, because there's a word and the subtree has one word right here. And real quick, let me just do it. So why not? Okay, so here there's also a 1 and a 1. So let's think about how numwords actually works. It's a subtree. The session is probably going to be maybe like 10, 15 maximum. So I'm going to try and go quick to this because I got to go. But yeah, but normally these sessions, I drag them out way past 9:30. So, okay, so right here, subtree is 1. If we think about it right here, there's no word. So I'm putting the flag for if it's a word on the left, and I'm putting the number of words on the right, just so you guys know. So this is not a word. APPL is not a word, but apple is. And this is the same thing for all of these other words. We're only assuming there's avocado, apple, and permission. So let's finish this one right here. None of these are words on their own, but their subtrees all have one word, which is this one. This one also has a subtree of 1, which is this one. Same thing with this one, same thing with this one. So that's where that 1 for the num words come. Same thing here, same thing here. Now here is where things are going to be different. A on its own in the stri, the example that they gave us, is not a word. So we're going to have a 0 on the left. But if we think about the subtree, A is not a word, right? So we're going to have 0. Then if we think about how many words are under us, like what is a subtree of things under us, we're going to have 1 on this side, and we're going to have another 1 coming up from this side, because we really have this right here. So 1. And that comes from this word down here, right? So that's how the whole subtree calculation things works. So there's going to be 1 plus 1 plus 0 is going to be 2. On this side, you're actually going to have a 2. So that is the whole idea right there. A is not a word. And I'm just going to do this real quick. So just bear with me. Okay, so this is what we're working with. By the way, the root node never has any counts or anything. It's just a dummy node, just holding the whole thing up. Because without this, you won't have any of this. Okay, so now let's go into pretty much the actual question. Now that we've set this all up, how it looks. They want to find all words with a certain letter, right? So let's traverse the try and see. Let's say we want to find all words with letter P. It's not words that start with letter P, it's words that have a P in them. So remember, these num words, it represents how many words are in the subtree of of a given node. So really what's going to end up happening is that you're going to go down. So we're going to traverse through it and we're looking for a P. So now we're going to go to P. We're going to see, oh, from A, we can reach a P, right? We can reach it. What we can do, because think about it, we have a word. So far we have A, and now we see, oh, there's a potential P we can add in. So, okay, we have A, and then, we have P. Let's see if going down P has any words under it. But we know from this point on, anything past here is going to have a P, even if we go deeper than it, because the path is A, P, and then, here, A, P, P, L, E. But we don't have to go all the way down to figure that out. At the first P that we find on any recursive path, we can just add the number of words at that node if it exists. So what I'm saying is, from A, you're going to see, okay, do I have a P? Okay, I have a P, then good. Why don't we just add it into the try? Like just take the number of words, so 1, and let's store it and add it. Let's recurse all the other ways we can go. So we're going to end up recursing, because at this point, we're going to stop. We're going to say, okay, let's take this answer at this P, because we know as we build out or try to build out other words, so we have A, P, P, L, E. We know that A and P has a P, right? We know that APP has a P because this P is here. Same thing with APPL. There's this P. Same thing with this APPLE. So Apple, because there's a P here. So it's redundant to keep going past this whole point and further and further. Because really, there's also no way to keep track of how many P's you've seen in the way that they set this problem up. So the first one, you're going to stop and just take the number of words at that subtree. So right here, we would have 1. So we have 1 returned up. On this side, there's no P anywhere. So we're just going to end up returning 0. So we're going to have 0. 0 plus 1, we're going to end up returning 1 up here. Right? So now we're going to recurse down the other path. We're going to see, okay, let's go down here. Do we have a P? Oh, we have a P from where we are right now. Let's just take the number of words in the subtree, and we're going to stop here. We're not going to go down anything of this. We're never going to go down. We're just going to stop at the first P, because permission, every way you chop it up has a P from the get-go, from the very start. So you just take this, and now you're going to have 1. And now you're going to see how many words have a P in it. So now we're going to have 1 plus 1 on this side. And our final answer is going to be 2. And that's how they derive the answer from that. So that's how they come up with the answer. So let's just code it out now that we understand what's going on. Okay, so we have the struct. Now, so it's a recursive function. So let's see. First of all, let's just have a quick little base case. Easy points make sense as well. Okay, let me not do not. Some people get confused with that. So if it equals null, return 0. Now we're going to have an answer variable to store. Okay, what are all the answers that I've gotten from all my children? Because remember, you might not find a P where you currently are at. So for example, you can say, let's say in this example we had here, let's say we had something like, let's say we're looking for all letter A's, right? You have a subtree, and then you have something like A, which is a word. Let's just say 1 and 1. That's it. Meanwhile, here you have a B, right? And then you go A, and then, there's a bunch of stuff under here. So you can't just stop at the first one. Like in this case, you just have to recurse through all of them, because you don't know where you're going to find an A in a word, so it's not always going to be at the start. So you have to end up recursing down all possible paths to get any possible word that might have a P somewhere, or any, whatever letter you're looking for. So you're going to iterate through all 26 children of the tribe. So as you iterate, you're gonna want to check, and there's gonna be a check that'll stop stuff in time, I guess. So let's just check if x equals. So remember, x represents whatever index in the alphabet you're at. So if x equals, and more importantly, x or a, well, actually, it's all lowercase. So a plus x, and a plus x equals alpha, meaning it equals whatever letter you're currently looking for. Then what you're going to want to do, and more importantly, if a plus x equals alpha and root children of a plus x does not equal null, then what you can end up doing is, so this is saying, okay, am I at the letter that I want to, or like, am I currently at that iteration? If so, and it does not equal null, let's reach down into it and see, okay, how many letters does it have that I can account for, or sorry, not how many letters, but how many children with a given letter do I have down that path? So we don't have to go down that entire path. Right here we'll have answer plus equals root children. So this is the reaching down part. We're just gonna look down. Okay, let's see how many you have, how many numbers you have under your subtree. So now at this point, else, you're just going to end up recursing down that way. So let's think about what are the possible breaking conditions. If both of these conditions are not true, that can only mean three things. One of these conditions is not true. So either this one's not true, or this one's not true, or both of them are not true. So let's say this is not true, only this is not true. We're not at the current letter that we're looking for, meaning it doesn't matter. We're going to keep on going because we can't just stop at this point. And right here, if it's not equal to null, then we can't arrow into it, meaning just keep on going. We're just going to skip it. And if we skip something that's null, it doesn't matter because it just equals 0. So we're all good there. If they're both false, meaning we're not at the right location, and it's also not null, it doesn't matter because you wouldn't go there either way, meaning it's equal to 0. So you're never, like, it's not going to change anything if any of these two conditions are false. If they're not false, or sorry, if either of them are false, you're just going to keep recursing because that means, okay, I can't reach down, and also I'm not at the right place. We're going to have answer plus equals strings with letter. Root children, we're going to go down whichever child we can, alpha, and that, oh yeah, and also outside of the for loop, we just return our answer. So just like I explained, it's going to aggregate like it did right here. It aggregated going down both ways. So yeah, in this example, it would have, instead of just stopping here, it would have ended up going, oh, okay. I ended up finding no letters of P. So that means the answer variable here would have been 0. Answer variable here would have been 0. 0 plus 0, 0. Answer variable here is 0. Because the whole thing, it didn't find a P in any of these subtrees. So eventually it'll return a 0. So that's why I didn't write it out. But it's going to be 0 plus 1, then return 1. So answer is currently 1. And now you're going to go to the next child, which the only one is P. And you're going to see, oh, a P. Let's just add 1. So now we have 1 plus 1. So answer is currently 1 from this recursion. Plus 1 is going to give us 2. And that's the whole logic. So go down paths where we don't have the letter we're looking for. Whenever we find the letter we're looking for, just stop. We don't have to explore the rest of the subtree. So we did that here. We did that here. We didn't do that here. So that's pretty much the logic for this.
For the root dash children, why is it the character A plus X? Wouldn't that make it like not in the index?
Oh yeah. My bad. My bad. There we go. So this is the correct answer. My bad on that. So let's check what they wrote. So looks like they did things slightly differently. So base case, that's good. Total, so this is their answer variable. They did their for loop, 26. And pretty much what they did, instead of going from I and adding that to the A, which is like the base where you're, that's what the letters represent. You start from A, lowercase a, which is 97, up until you add 25, just 121. That's Z in lowercase. But you don't need to know the numbers. Then it just says equal equals alpha. So just saying, okay, is the index representative of like what letter I'm at? Is it equal to alpha? So what they ended up doing, they just ended up subtracting. They ended up pretty much putting alpha minus A is going to be in the range 0 to 25 inclusive. So they just brought it down to the level of the iterations. Meanwhile, here we just went up, I guess, in terms of the alphabet. So we went up on the alphabet, they just went down. So it gives you the same thing. And they also check if root does not equal null, because then if it's null, then you can't reach into it. So they just did two ifs. I just put them together, but you could have nested them as well. But same difference, same logic. Else recurse. So, and then return total outside. So that's about it. Okay, let's do one more real quick. And then I'm going to go to stacks and queues real quick, just do one or two questions on that. So write an iterative non-recursive function that takes the root of a trie and string and returns the number of new nodes we would have to add into the trie in order to insert the string. You may assume string is not null, not empty, and contains lowercase alphabet. However, you must handle the case where root is null. Okay, so whenever they tell you certain things like that, just do it right away, if you can. So they're saying root is null, but they also give us special restrictions. So let's just take note of these restrictions. And the root is null. String will be non-null. Lowercase. Okay, so no pointer math. So no pointer arithmetic. Don't change this trie or string. And don't call string length repeatedly. So if K, and if you need to do it once in your whole function. Okay. Okay, so we're trying to figure out how many words or how many new nodes we're gonna have to, or letters, I mean, how many new letters and nodes we're gonna have to add in if we add in a certain word. So let's think about a certain trie. Say we have a word A, right? So we just have A. If we want to add the word app, we would, so we already had this right here, but what we ended up adding was this whole thing right here. So we would have had to add 1 and then 2 nodes. So how can we calculate that? Let's think about it. So we would have had, actually, yeah, let's just try like this. So we can take the length of the word. So app, length of the word is equal to 3, right? So let's see a couple of things we have to consider. Let's just compare this to what we currently had. So we had length of just A. We had 1, right? So 3 minus 2 is going to be equal, or sorry, 3 minus 1 is going to be equal to 2. So in this case, okay, we only have to add 2, but there's an edge case that some people might have caught or might have not considered. What if the thing is empty, right? The whole thing is empty. Or let's say let's just go case by case. So in this case, we only have to add 2. So we had 1, we needed to add 2 to get 3. Now in this case, let's say we want to add app. Okay, we have nothing to go off of. Meaning we're going to have to add our A, our P, and our, okay, it looks like a linked list. My bad, guys. It's a try. A, P, P, right? So there's 3 we have to add. But on the flip case, let's say we didn't even have any of that. So let's say we just had nothing. We just had nothing. It's just null. So if it's just null, then we have to create the root node. That's important. Create the root node, then the A, then the P, then the next P. So we have P, P, A, and then this is the root node. So we didn't have to create 3 just because it's app. We had to create 4 because the root node holds up the whole trie. That's something to remember. So that's one of the things where they say, oh, handle the edge case with that. So that's something to think about. So we can handle this a couple ways. So let's just hop straight into the code and see like what we're gonna have to end up doing. So there's multiple considerations. We know how we can deal with if we don't have, if it's just null, just add 1 to the length of the string. Meanwhile, if we're not missing anything, or if we're not missing this right here, we can just take, like in the app and the A example, we can just take the length of the 2 strings, right? So 3 and 1, subtract them. Okay, subtract them, and then that'll give you this right here. So that'll give you the answer. So there's just 2 things you got to handle. Yeah, that's the wrong code. Okay, new node count. Okay, so we only have to call, we can only call string length once, and we know that it's going to be non-null. So let's just do that now. Length is going to be equal to string length of string. Okay, so now we have the length. Let's handle right off the bat, because now it's going to be weird. Let's just handle right off the bat. Root equals null. We're just going to end up returning length plus 1, because we know we have to account for the length, the number of nodes we have to add, plus 1 for the root that holds everything up. So that's one case done. We know that that case is out the door. So done, right? Let's just delete this stuff. We don't necessarily need it in this panel, but I'll write it here. Let's see what else we're working with. So this is done. String will be non-null. Okay, that's just you know, restrictions, no pointer math. Leave the try alone, call it 1. So we've kind of satisfied everything. Now we just have to think of the logic. So if we're doing iterative, we're going to have to traverse the try somehow. So the way we can do that is we can, what I like to do for every single function, make a temporary like try node. So me personally, I like to call these things C. So C for current. I'll just call it current because, you know, people might not be used to that convention. So this is currently pointing at the very top of the try, so at the very top of it. So another thing we're also going to need is an index, because the whole thing is that we're going to want to see, okay, what if we get down to a certain point and then we can just stop? Like, okay, we know that we can't keep going past this point. Like something's going to be null. So let's say when we had AP, or sorry, just A, we could just stop right here because we did not have any of this. So we could stop and say, okay, so we've done 1 iteration, and now what we can do is just do 3 minus whatever this index is, and that'll give me the answer. So we're going to need 2 variables really, 1 for traversing and 1 for keeping track of how many, how can I say, how many iterations we've done. Because that'll pretty much, like, I guess, unlock or hold whatever our answer is going to be. And really, the way you're going to check whether or not you can go down a way is just see, okay, from here, can I go down to the next letter? If I can, okay, then I'll stop. If not, keep incrementing. So we're going to have our index, let's call it X. And now at this point, let's just, while X is less than, because we don't want to go over the word, so while X is less than length, now we're going to end up doing is moving current down So current equals current child. And how are we going to guide where we're going to go? We're going to do that based on whatever x is. So we're going to have string of x, meaning the current letter we're at, minus a, because it's all lowercase. And remember, the try has only, oh shoot, I just hit the try has 26 locations. So this will end up giving one of the 26 locations, right? We're going to end up guiding it where we have to go. And now at this point, this is where it's going to get a little weird or a little tricky. Because what I'm going to do here is I'm going to have an if check. But I'm going to increment at the very end. But at first, I'm going to have an if check. And you guys will see why. So I'm going to check if current does not equal null. Then right here, or sorry, if it equals null, what I'm going to end up doing is just returning, or actually let's just break out of it right here. And let me just explain why this is the case. So we have this variable that's going to keep iterating while we can go down certain paths for a word. But let's say we get to a point right here. Let's say we get to where we're going to add the word. So we get to A, and then there's no P. We're going to add an app, right? So these two are not here. So if we iterate first and then we move it down, we're going to go from here to here, which is null. So this is where we're going to be. This is where current is at. So the thing is, if we increment our variable, our counter variable, right here we're at index 1. Now we're going to be at index 2. If we increment first, then it's going to count as if we had a second letter, but we actually don't. So that's why I'm doing the if check first. If after we move, we end up at a null node, we don't want to increment first, because if we increment first, then really it's going to make it seem like, oh, we did the length of this, which is going to be 3 minus how far our iteration got, 2, 1. But really, if we're adding app right here, we're going to have 2 letters. So that's why you do an if check to see, okay, if I move it down, or like after I move it down, am I null? If I'm null, just stop. So you increment after you end up checking that you're not null. Because if not, then you're going to count for a letter that is actually not there. So you break, and now what's going to end up happening is you're going to end up returning the length minus x. So in this case, let's just follow what we were saying. What's going to end up happening, we're going to see, okay, we're null. So what's going to happen is we're going to see our index ended at 1. So now we're going to take the length minus 1, which is how far we got. So the total length of the word minus how far we got, how much things we saw. And then this is going to end up giving us 2, which is actually what our answer is. So that's why you do a break. Alternatively, you could have done the return for that in here, and then just return 0 at the end. Because think about it, the only time this will ever happen is if some letters are missing. Meanwhile, if no letters are missing, this will never break. If it never breaks, it'll stop by this right here, like this x less than length. And at that point, you verified that every letter is in there, so you can just return 0. So that's the whole idea. But I like the break style better, honestly. So let's see what the answer is. Yep. So string length, iterate. They did a for loop. I did a while loop. If root equals null, so they actually ended up checking first, but the way I set up my code, I'm using while, so I'm not using a for loop. So I have to increment myself. And they did the same idea, but I end up moving first and then checking. They end up checking and then moving. So same exact thing. And like I said, if you get past this for loop, that means every letter's in there, so they return 0. But it's the same logic. Just imagine if this never hits, this is x is, remember the breaking condition, since you're incrementing by 1, you'll stop once x is equal to the length. And if x is equal to the length, length minus length is still going to be 0. So it still ends up working out. So that is how you get that answer. Hope that made sense. So right now I'm just going to do a couple questions on stacks and queue, just one or two because I gotta go soon. But okay, so let's just hop into this question right away. So suppose we have a stack implemented in a linked list. The stack structure contains a pointer to the header linked list to indicate how many items are on. It's a stack. Write a function that will pop up the contents and push them onto a newly created stack, returning a pointer of the newly created stack. Now, in effect, your function should reverse the order of items in the original stack, place them on a new stack. So you have access to all the usual stack functions. Okay, so let's just draw this out. Remember, stack, LIFO, last in, first out. So as we add stuff in, the first thing will be out. So for example, if we add in 1 and then 2, 2 comes out first, then 1, etc. So if we want to reverse a stack, let's think about what we have to do. Reverse a stack and put into another stack. So all we have to do is literally just we just pop something off and place it into the other stack. Because think about it, if you have last in, first out data structure, what's going to end up happening is by placing the last thing in first, you can kind of reverse that logic. It's kind of like first in, first in, last out, if you think about it like that. So instead of last in, wait, did I just repeat the same thing? So okay, last in, first out. But really, okay, the first thing in is going to be the last thing out. So first thing in, last out. Okay, Philo. I mean, I guess, but that's really what's going to end up happening. So since it's a LIFO data structure, for you to reverse the order, since the first thing in is going to be the last thing out, assuming you don't add anything else or whatever, then all you have to do is just pop. That's going to be 3. Pop. That's going to be 2, and then pop. That's going to be 1. So now our stack is just 1, like from top to bottom, 1, 3, 2. It used to be 3, 2, 1. So think about it. The logic applies. If the last thing in is the first thing out, the first thing in has to be the last thing out, because if not, then how can the last thing in be the first thing out? So that's kind of like confusing, but I hope that made sense. I'm kind of like applying the property, but kind of looking at it in reverse, and it still holds. So what you're going to have to end up doing right there is doing just that. So let's get this code real quick. Okay, so let's just hop straight into it. We're just going to reverse the stack. So we have a stack. I don't know if they say to free anything. It doesn't seem like they say to do that. So, okay. Yeah, they don't say to free a stack, I guess. I'll just do it either way, because why not? Okay. So we're just going to use the function that they give. So while, so for you to fully transfer one stack to the other and have it reverse, you just need to go while it's not empty. So while stack 1 is not empty, so S is not empty. So while we still have elements, remember, we're just gonna pop, 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 and once there's nothing in, oh yeah, pop in place, pop in place, pop in place. Once there's nothing in here, then we're done. So that's what is empty is gonna do. It's gonna stop whenever it's just empty. So while that's the case, what we're gonna do, we're just going to use the push function, and we're gonna push what we ended up popping from S. So I'll just write it like this. Pop from S equals pop S. And what we can end up doing is just push push onto the stack, the U stack. Oh, and by the way, there's some things that I forgot, but I'll do that in a minute. So new S, and now we're gonna have to push on what we just popped off from the other stack. So what did I forget? Notice how they don't give you an initialization function, so you're just gonna have to initialize it yourself. So for example, new S, what does it give us? So this is a stack. So the stack has a top. You're just gonna start off at null because it's gonna be empty, and set the new S stack to size 0. And now from this point, okay, we've initialized everything. The functions will work properly. And we just transferred everything over. By the way, you don't have to write it like this. You can write it like this as well. That's how I would have done it, but U to U, it still works the same way. And okay, so from this point, you're just gonna end up returning the stack that you just created. So US. And I'm not really sure if they say that if you have to free the stack. Okay, it doesn't really say, but you know, it doesn't hurt anyone, I guess. So let's just do US, and that's about it. Just see what the answer is. Yeah, so you just initialize it, and then while it's not empty, then you just push, you just end up popping up onto the other stack. So they don't free it, but I just did. But I mean, don't make any assumptions. It's probably the best way to look at it, you know. And that's 10 points right there. I'll do one more and then I got to go. Okay. So this one is going to take a while to do. This one as well. Okay, let's do this one. So we wish to implement a queue using an array. The structure of the queue is as following. So the queue contains 3 attributes: the number of elements, the front, and the maximum capacity. So write a function to implement the dequeue functionality for a queue while ensuring that no null pointer error occurred. Take in one parameter, the pointer to the queue, and return what was dequeued. If the queue is null or there's no elements, return 0. So for these type of functions, let's just, before I explain the whole logic and everything, let's go straight into what we know we have to do real quick. And typically that's base case. So let's write the base case real quick. So let's think about it. If the queue is equal to null, or the queue number of elements, they're not giving us any special functions to use. Equals 0, just return 0. So that's it. We have the 2 bases right there. So there we handled that. You can break this up into 2 ifs, like one if in here, like q equals null, another if here, but I like to compound them. Okay, so now the next thing we have to dequeue. So let's think about how a dequeue works. This is, by the way, is a circular linked list array implementation. So the whole idea by that one is, let's say you want to add some elements in. So let's add in a couple numbers, 3, 6, 9, right? So 3, 6, and 9, right? So we're good. Our front is here. Our number of elements is 3. F is 0, so that's our front. But let's say we want to dequeue, right? So let's say we want to dequeue something. And that means our front would have to move forward here, but we'd have to keep this value. So we keep the value. So let's just take this value 3, return value 3. And then what we're going to do, we're going to increment it forward. And now the number of elements is going to be decreased and F is going to be moved up. Now let's just do it again. F, and this is going to be 2, this is going to be 1. So this is where the whole idea, and by the way, when you dequeue, these values are going to stay here. You can replace them, so we can just like scratch them out to signify that there's nothing there. But Yeah, when you end up adding stuff later on, it'll override it. But the whole idea now is, let's say I want to DQ, or actually, let's say I want to add an element, right? So if I want to add an element, I would end up doing, it'll be a little complicated, but we know that the next available spot is going to be right here. That's the whole point of a circular queue. So let's say we want to add 10. So 10 would end up going right here, okay? So we have that there, that's 10. Let's just erase this. So we have 2 elements. Now, let's say we wanted to DQ here. This is where the whole circular queue thing comes in when it comes to DQing. So if F is here, think about it. Sure, we can take the value that we have to return. It's going to be 9. And now at this point, we can end up incrementing. But while we will be good in this iteration, right? Well, because we were able to get 9, which is what we DQ'd. So our front will now be at 3. Our number of elements would now be at 1. What ends up happening is that by us just incrementing it and not like doing anything, we're just going to, on the next iteration, it's going to index into here, and you know, you're going to segfault. So you don't want to segfault. So what you're going to do at every iteration, you're going to take the front, so Q front plus 1, and then you're going to mod it by the capacity. So why does that work? So right here, this is typically the main case. It's always at the end. This is where everything messes up. So if you do F plus 1, so that's going to put you at right here, right? And now if you modulate this, so this is 0, 1, 2. You were previously at 2, now you're at 3. So if you do 3 mod the capacity, 3 mod 3 is equal to 0. That's going to modulate it and say, okay, your front is not going to be equal here. So really the formula for DQing is really just this right here. F is going to be equal to what F currently is plus 1, and you mod that whole thing by the capacity just to handle the case where you're at this element. It's nothing else aside from that. Really, you can handle this with just an if check. If I'm at the end, you know, then put me back at 0, set equal to 0. But generally people use mod for this. So that's like the whole idea behind the formula. So yeah, for DQ, that's the whole idea. Take the value, put it into this formula. If you remember this formula, you can DQ on a circular queue. So now right here, we're just gonna take answer. So this is gonna be what we're gonna return. So this is gonna be Q of what is it? Array of front. Now at this point, we're just gonna move the Q front forward. And right here, we're gonna remember we have to decrease the number of elements. Okay, minus. I like to do the parentheses just to be safe. And at this point, we're just going to end up, the capacity stays the same. The only thing that changes is front and number of elements. And now right here, we're just going to return the answer, which is the value that we just DQ'd, right? And that's it. That's all it is. So let's see. Check if Q is null. We did that. Check if number of elements is 0. We did that. To store the right value, return value. We did that. Update circular logic. We did that. Q number of elements minus 1, and then return the return value. So that is that. By the way, let me just do Q real quick before I go. Not on Q. So I'll explain this before I go. But yeah, guys, this is going to be the last question. So you guys know. So if Q equals null, it's going to want to return, let's just say 0, meaning we couldn't do it. And at the end, we're going to return 1, meaning that we could onQ it. And if we want to onQ, really what ends up changing is, let's say you want to onQ right here. So let's say you have something like, let's say you have the front right here. Let's say you have 3, there's nothing here. right? And then you have 10 right here. So of course, number of elements is num elements is 2. Our front is index 2, cap is 3, and yeah, this is our array. So let's just do some math and see what happens. So if we take the front, so we're gonna do 2 plus the number of elements 2, then we're gonna be at 4. But our array goes from 1, 0, 1, 2, and then 3 and 4. 3 and 4 are out of bounds. So we're gonna have to modulate this just like we did the other one. So mod it by the capacity, which is 3, and that'll put us at 1. So that pretty much takes us from this index right here and says, okay, we're gonna do 2 plus the number of elements, which is 2. That'll put us at sorry, not at this location right here, at index 1. So that'll put us, it really does this and stops right here. That's kind of like the whole logic of circular. So really it says, okay, this is where we're going to be placing our elements. So the way this works is you take the front plus the number of elements, because think about it, that's kind of how many things you have in sequence. So you take the where you currently are at plus the number of elements, mod it by the capacity. So that'll adjust it based on, okay, I've gone past. Let me say, am I here? Am I here? Am I here? Etc. And it'll point exactly always to the next available spot, of course, unless you are full. In the case that you're full, let's say you have something here, then you're gonna do 2 plus 3, which equals 5, mod 3, and that's gonna be equal to 2. And by the way, 2 is equal to your front. So that way you know you're full. So that's an easy way to check. Alternatively, you can also check if you're full if your number of elements is equal to your capacity. So that's 2 ways to check. But that's like the whole idea. So you're going to want to have a check to see if you're full. This is the easiest way to check these 2. And that's kind of like the way the whole circular logic works for on-queuing. You're just going to do the front plus the number of elements, mod by the what do you call it, by the capacity, and place it in that location. So that was a pretty quick explanation, but I hope it makes sense. This is what it looks like in code real quick. And there we go. So if we're null or if we're full, stop. And now we're going to end up doing is just doing we know that we're not full, so we have a space that we can fall onto that's not the front. So now we can do Q of array, Q of front, plus Q of number of elements, mod capacity to wrap back around. And now we're going to be at the perfect spot, the next location after the last spot. Set that equal to value, increment the number of elements, and that's all you got to do. By the way, these 2 questions, they come up as 10 pointers. So really, as long as you memorize, I wouldn't say memorize, but understand, but you know, you got to do what you got to do. As long as you memorize these 2 right here for DQ and OnQ, that's all it is to get these circular Q questions down. There's really, there's never been really any other type of question about these. It's just OnQ, DQ, that's about it. That's the main functionality. And yeah, that's pretty much it, guys. So that is officially the last session for this. I'm probably not going to do another foundation exam review because, you know, I did the night hacks and I covered a lot of questions already. I've done these 5 sessions, covered a lot of the same questions already, but you know, things are different now. I made the website. I'm able to, like, you know, do things you know, more efficiently. You know, and you guys are also able to study with this. So I hope that the night hack sessions, the SHPE sessions, and this website have been able to make an impact on, you know, you passing, helping you pass. So yeah, guys, I'm gonna call it a night here. I gotta go pick up someone from the airport, but yeah, I wish you guys good luck. Good luck on the foundation. Definitely let me know how you felt after the test. And yeah, that's about it. Wish you guys luck. Peace. Thank you. Good night.
Thank you.
Yeah. See ya.